Hello everyone, course IoT. I'm Neda and today I'm going to talk about Raspberry Pi Pico programming examples. I prepared 6 examples and we will go through each of them to learn how it works. So let's go to the first one, file structure. In MicroPython programming, we need to organize our code in these 3 files, boot.py and main.py and readme.txt. When Pico starts, it looks for boot.py. This script is executed when the Pico boots up and sets up various configuration options for the Pico W. Whatever you want to put in these files, but normally we will put network setup config. And the next one is main.py, and this is the main script that will contain the MicroPython program, and it's executed after boot.py. In MicroPython firmware, I mean that file that is called UF2 file, and we learned about it in the previous lectures. These 2 files, boot.py and main.py, are specified. So that's why we always have to have the file names as boot.py and main.py to be recognized by the Pico firmware. And in readme.txt, this file contains some very basic information about the program that you write for your Pico. So let's see what is the steps. First of all, you should create a folder and name it example1. For simplicity, I start and learn it example1 to 6 for these 6 examples. So after creating a folder, you need to create a file and name it boot.py and write the following code that is in the next slide into your boot.py, and then you should create another file and name it main.py and write the following code that I will show you in the next slide, and then upload your project example1 to your Pico and check the terminal. Be careful before upload. You need to first configure your project that you first of all you need to connect your Pico, and then you configure it and then upload your project. So the MicroPython boot.py, the code is very simple, is like this. I just want to show you in here that you will see when it is running, it's a start to run, you will see this hello that is from the boot.file, and after that you will see this hello that it is from main.py file. So if you write these 2 code in these 2 different files, when you execute it, you will see that, okay, first the hello from boot.py you will see, and after that you will see the output from the main.py. It shows that first boot.py is executed and then the output of main.py is shown in the output. But the code is quite simple. We need to import time module that we learn about it. Actually here it's MicroPython, and then you can use macro time, and after that you can use the time.sleep. So let's go to the next example, that is onboard LED, and we get to work our Pico W in I think in lecture 2, and we could see that LED is blinking. Making an LED light up is a traditional introduction to learning physical computing, like macro Python programming. But another reason is that you can get started without any additional components. That's why we always start with this simple example. And as we have seen before in lecture 2. The Pico has a small LED, and this is in the top of it, and this onboard LED is connected to one of Raspberry Pi 2040's GPIO, or general purpose input output pins, that it is GPIO 25. And if you remember the Pico W pin out diagram that we've seen all of it together, this pin is one of the missing GPIO pins present on RP 2040, but not broken out to a physical pin on the edge of your Pico. So while you can't connect any external hardware to this pin other than the onboard LED, it can be treated just the same as any other GPIO pin within your programs, and it makes a great way to add an output to your programs without needing any extra components. We are going to write a MicroPython program that toggles, flash LED on and off, and toggles the state of the onboard LED connected to GPIO pin 25 of Pico W every 5 seconds. So the step for it is that you need to create a folder and name it example2, and create a file and name it boot.py, and write the following code that we will see in the next slide, and create a file and name it main.py, and write the following code that we will see in the next slide, and upload your project to the Pico W and check the terminal. So let's see here. We have import machine and import time. First of all, we need to import the required libraries: machine for GPIO pin control and time for the time delay. We shouldn't say U, it's written U, but you should read it macro time, because we are in programming, we are doing MicroPython programming, so the time is macro time, the library. After that, here in line 4, we initialize a pin object with the number 25 and set its mode to output using machine.pin 25 and machine pin output. But what does it mean? What does it mean when we say pin.output should be is set to the mode of a GPIO pin to output? What does it mean when we set it to output? GPIO pins can be either inputs or outputs. We learned it before. And input pin receives signals or data from another device, whereas an output pin sends signals or data to another device. By setting a pin to output mode, we can control the voltage level on the pin to send signals to another device. When we use pin.output in our code, we are telling the microcontroller to configure that particular pin as an output pin. After setting the pin to output mode, we can then use pin.value to set the voltage level on that pin to either high 3.3 volt or low 0 volt. So that is why we need to set the pin as out. And after that, we enter a loop that repeats forever. I will tell you what is the logic behind this, putting this in the loop and creating an infinite loop. The reason is that on full computers that run operating systems like Linux, Windows, or Mac OS, programs usually run, do their job, and then terminate and return control to the operating system. In this way, many programs are run all under the control of the operating system. And the operating system is the only program that runs from power on to power off. On microcontrollers, typically there is no operating system, and the only thing that runs is our program. The expectation is our program will be run shortly after that our Pico W powers on, and then terminated when it is power off. That is why we create an infinite loop that runs forever, which is typical of most microcontroller programs. So you will see we will have loop, infinite loop in our macro programming uh, physical computing for the microcontrollers. So after that, we enter the loop. We toggle the state of the LED, I mean the LED on board pin using LED on board dot toggle, as you can see here. And this alternates the LED between on and off states on each iteration of the loop. And then we delay the execution for 5 seconds using utime.sleep 5. This is 5 seconds to keep the LED on or off state for 5 seconds. And then the loop repeats indefinitely and toggling the LED and delaying the execution every 5 seconds. So that is whole story about how we should use the machine library, the pin library, and how we should set it, and how we should use the GPIO pins, how we should use the time library, and then why we have the while infinite loop. So here there is a macro time versus time that I explained. That is a macro time. We are using a macro Python programming language, and time that is using Python language. But here is mentioned that if you forget and use import time, you shouldn't be worried, because MacroPython will automatically use the utime library instead, as you saw in the previous here. We import time, but it will use macro time. So the example 3 is temperature and humidity reading. How we are going to read the value of temperature and humidity from our sensor DHT11. First of all, you need to create a folder and name it example3, and create a file and name it main.py, and write the following code into the main.py that we will see in the next slide, and create a file and name it dht.py. This is a library for working with DHT sensor. So we will use this library for working with this sensor. And then you need to write the following code into the dht.py and upload your project, that it is example 3, to the Pico, and then check the terminal output. I explain again here that libraries are a collection of a code that makes it easy for you to connect a sensor, display module, etc. Like here that we are going to use dht.py. For example, the liquid crystal library makes it easy to talk to the character LCD display. And there are thousands of libraries available for download and working with sensors and electronic components. First of all, you need to import the required libraries that here you can see pin from the machine module for GPIO pin control, and time for time delay. I2C, as you can see, is not bold like the others. It's gray, and it means that we are not using it. Like invalid checksum, so we don't need to import this here. And also we need import the DHT11 from the DHT module, and for reading data from the sensor. So we need to import these three libraries. After that, we config pin 28 as an output pin with a pull down resistor. So let's see, what does it mean? What does this pin dot pull down resistor mean? We learn what is pin dot out, but I explain again. Pin dot out is used to set the mode of a GPIO pin to output. And GPIO pins can be either input or output. An input pin receives signals or data from another device, whereas an output pin sends signals or data to another device. And by setting a pin to output mode, we can control the voltage level on the pin to send signals or to another device. When we use pin.output in our code, we are telling the microcontroller to configure that particular pin as an um, output pin. So this is what does pin.out mean. But what does pin.pulldown mean? In MicroPython, pin.pulldown is used to enable a pull-down resistor on a GPIO pin. A pull-down resistor is a component that is used to ensure that a pin has a predictable voltage level when it is not being actively driven by the microcontroller. When a pin is not being actively driven, it can be susceptible to noise or interference that can cause its voltage level to fluctuate, which can cause unpredictable behavior in a circuit. By enabling a pull-down resistor on a pin, we can ensure that the pin is pulled to a known low voltage level when it is not being actively driven. And this helps to stabilize the circuit and ensure that the pin behaves predictably. So when we use pin dot pull down in our code, we are we know that we are telling the microcontroller to enable a pull-down resistor on that particular pin. And this can be useful in situation where we want to ensure that a pin is at a known and low voltage level when it is not being used. But maybe someone asks, what does not being actively driven mean? What is the actively driven means? And I should say that actively driven refers to a situation where the voltage level on a pin is being controlled by a signal from the microcontroller. And in the case of a GPIO pin, actively driven means that the microcontroller is either setting the voltage level on the pin to high, I mean 3.3 volt, or low, 0 volt, or is rapidly switching the voltage level between high and low to create a signal or data transmission. When a pin is not being actively driven, it is left floating and can be susceptible to noise or interferences, which can cause its voltage level to fluctuate, and this can lead to unpredictable behavior in a circuit. So to avoid this, we can enable a pull-up or pull-down resistor on the pin, which will ensure that the pin is held as at a predictable voltage level when it is not being actively driven. So after that, in line 6, we initialize a DHT11 object with the configured pin. This is this variable that we configured here. After that, mm, we enter a loop that repeats forever, and I explain why we need this infinite loop. So here in time.sleep2, we delay the execution for 2 seconds using time.sleep2 to avoid reading the sensor too frequently. And here we are trying to read the temperature value from the sensor using T-sensor temperature. And if an exception occurs, print we will here we will print mm, um, an error message and continues to the next iteration of the loop. And here I think in the code that I put in the apply IoT LNU, you can find the complete code, and you will find it with the try and accept. So let's continue. We were here. So here we try to read the sensor, the humidity value from the sensor using this line. And after that, we will print the temperature and humidity um, value. Value using the print function, and the loop repeats indefinitely, reading and printing the data every 4 seconds. So this is all about the code, how it works. The THD.py code you can download from here if it's not visible here, and for sure we need it. This is the library for working with this sensor, and all the project code you can find from this link, from IoT LNU, applied IoT. And if you go to this tree master, you will find your course code here, and you can find the code from this link. The wiring diagram for using the DHT11 sensor with the Raspberry Pi Pico W is like this. We add one pull-up resistor between the pins, 3 volt 3, and the signal, that is GPIO 13. You can see here. And if you use a resistor, the resistor should have a resistance of between 4.7 kilo ohm and 10 kilo ohm. If you are working with the sensor, you need this resistor, but DHT11 can work without a resistor if we define it in the software, because Pico W pins have internal pull up and pull down resistor. So in our case, we don't need any resistor. As you can see, I didn't use it myself. So it's possible to use any output pin for your project. For the sake of an example, we use GPIO 13, and depending on your model, you may need to adjust the circuit accordingly if you are using another GPIO pin. And this is the how connection is done in the FreeSync. And this is how we are reading the temperature, and overall setup is here. And this is the output, humidity 25 and temperature 23. You should see in output like this, that your code is regularly reading the temperature and humidity value of the sensor. And if you encounter the the error, invalid pulse count, expected 84 but got 82 pulses, message in the terminal, you need to add a try and exception to the code. So that's why when I was explaining the code, the first code here, we don't have any try and except, but you need to add it, because you will get invalid pulse count error, and it's nice to add try and except try when you are reading the values. So if any error happens, it will catch it, and then it will continue to read the next value. Okay, the next example is ADC, analog to digital converter. And we will use a photoresistor sensor. So projects running different actions in function of sun exposure usually need to acquire information on the light level as a trigger to execute specified tasks. A photoresistor with Raspberry Pi Pico W can provide light info by acquiring analog levels from its input pins. A photoresistor is also known as a photocell, and it is an analog sensor, and it is also a light dependent resistor, LDR. As the name suggests, these components act like a resistor, changing their resistance in response to how much light is falling on it. Usually, photoresistors have a very high resistance in near darkness and very low resistance in bright light. This property makes photoresistors useful in a wide range of applications, such as automatic lighting controls, light meters, and camera exposure controls. As this sensor works as a simple resistor, you will not get absolute light values, for example, lumens. And compared to a reference voltage level, and that is the 3.3 volt provided by Raspberry Pi Pico W, you will read a value minor or equal to Vref reduced proportionally to the light exposed to the photoresistor. With ADC module, I mean analog to digital converter from MicroPython, this value will range between 0 and 65,535 for a 16-bit, and the maximum value is 65,535. So the steps is that create a folder and name it example4, and create a file and name it main.py, and write the following code in the next slide into the main.py, and upload your project example4 to the Pico W and check the terminal output. So here we are reading the analog output voltage of a photoresistor using an analog to digital converter, and prints this every 1 second. First of all, we import the required libraries, and as you can see, we import ADC and pin from the machine module or library for ADC and GPIO pin control, and sleep from the time module for the time delay. So we need these modules to work with the ADC. And we set the GPIO pin number for the ADC input to 26, and as a photo pin, I call it. And then here I define a function as a read light that takes the photo GP as a parameter, and inside this function we create a ADC object with pin number 26 to read the voltage from the ADC pin. And here we read the voltage using photores and photores.read micro 16, and which returns the voltage as a 16-bit integer value ranging from 0 to 65,535. And 16 bits, how we get this number? 16 bits means 2 bytes. Each 8 bits is 1 byte, so 16 bits is 2 bytes. And if 2 power so if we get all of this 16-bit as a 1 and you do this multiplication that we learned in the previous lecture, so you will get this number. And then here we return the integer value as the light variable here, as you can see. And then we have the return. In this function, we return the light, this variable. So where this function is called is in the while loop. We enter the while loop and we print light as a read light. That is our method, and we call it with this parameter. And this parameter, it pass here to this method as argument photo GP. So when we call it, this will run and start with photo pin 26. Your program start here, and it doesn't execute this part, this function, until it is called. Someone should call it because it is a function. So we come here, photo pin is 26, and when we come to the while, when we say read light photo pin, it will call read light 26, and we will come here, and then these commands are executed, and then return light. So light will be here and will be printed, and it's sleep delay the execution for 1 second using a sleep one to avoid reading the sensor too frequently. And this is the wiring diagram for using a photoresistor sensor with a Pico W. And you can see here we are using a if you're going to do this project, you need to use a resistor, and this is our photoresistor, and then we are connecting 3 lines to the pins and one of them is power, one of them is ground, and one of them is connected to the ADC pin of the Pico W. So the output will be like this, that lights is changing, and if you put your hands on the lights, when it comes darker, the value will decrease, and when it is more light, the value will increase. And you can go and try it. So the next example is Wi-Fi. In this example, we will show how we connect our Pico W to the Wi-Fi. So the steps are create a folder and name it example5, and create a file and name it boot.py, and write the following code in the next slide related to Wi-Fi into the boot.py, and upload your project example5 to the Pico W and check the terminal output. So this is the code for connection to the Wi-Fi, and you should put it in the boot.py as I mentioned before. Wi-Fi configuration related to the network stuff should be written in the boot.py. So when you execute this code, you will see the connection successful here, which means that your Pico W is successfully connected to the internet via Wi-Fi. But how it works? We need to use the network library, and we learned that network library in the previous lecture, and here we need to set our SSID and password of the internet. So the SSID that here we have is IoT Lab, and the password is modem that we put here, and you should put your everywhere you are, anywhere you are, you need to use that SSID and password that connect your Pico. And then we say station network dot WLAN network dot as a station underline if. And we activate and we connected via this two parameters, SSID and password, that we set it here. And in the loop, in the while loop, while a station is connected equals false, it says that pass. It means that until it's not connected, you should pass. That when it is connected, then it will go and print connection successful, and then you will see the output that there is a connection successful. And you can get your IP address, like the Linux when you are working ifconfig. You can get your IP address also here. So let's see the example 6 as a socket. In MicroPython programming, a socket is a way to establish a network connection between two devices over the internet. A socket is a software endpoint that allows two programs to communicate with each other over a network. A MicroPython sockets provide a simple and consistent interface for creating and managing network connections, and the socket module in MicroPython provides a set of functions and classes that can be used to create and manipulate sockets. Using sockets in MicroPython, you can create both client and server applications that can communicate with each other over a network. For example, you could create a MicroPython script that runs on a Wi-Fi enabled microcontroller and connects to a remote server to send and receive data. And we are going to see this example here now. So the steps is that create a folder and name it example 6, and create a file and name it boot.py, and write the following code under the Wi-Fi part. So we had in example 5 the Wi-Fi code. So you are going to put this code that is related to socket under the Wi-Fi code and upload your project to the Pico and check the terminal output. So here in this example, we import socket library. We need to work with socket library here. So we have an address variable, and it gets this address, DNS address, macropython.org with port 80, and it says that socket .socket and open a socket, and it connect to this address and send a request as a GET request with the HTTP protocol and in the application layer, and then connect to this server, I mean macropython.org, and receive 1000 byte of data that you can see here. It can receive more data if you set it the bigger numbers, but I set it here 1000, so you can see here we have 1000 byte of data. And then we print this data, and then we close the socket. So this is how the socket programming works. And sorry, I was explaining here. Hopefully you could see what I talk about, and then it was all about this slide, and then we can see the output here. And this is the whole code for Wi-Fi and socket. That this is the part that we wrote for the Wi-Fi connection, and this is the part for the using socket. So socket are an important feature of MicroPython programming that enables communication over the internet and allows MicroPython programs to interact with each other devices on a network. So for hands-on, please reading the temperature and humidity values of your DHT11 sensor and connect your Pico W to Wi-Fi as we did here. And with the current knowledge, you can do the projects of chapter 4, 5, 6, 7, and 8 of the reference book that I mentioned in the course press, and you can do more exercise. So, uh, and also you can access all examples of this lecture using the following link. All the examples that we had, all the source code, you can access using this link. Overall summary of whole this lecture, because this lecture is finished, it was in 5 parts, prepared in 5 parts, and it was the last part that we taught. And the whole things that we learned was the basics of the MicroPython programming language. We got to know what is the VS Code ID and how to use interactive console to interact with the microcontroller. And we learned about the MicroPython libraries, and we learned the file structure and program the Raspberry Pi Pico W microcontroller in MicroPython. Also, we learned how to work with analog to digital converter pins, and we learned how to connect the Raspberry Pi Pico W to Wi-Fi, and we learned how to work with the socket library. So the next will be messaging protocols and data formats. Thank you for your time, and I hope you enjoyed it. And if you have any feedback or question, please write me on a Slack group channels. And you are always welcome to my office or in IoT lab in Kalmar. Goodbye.